Hello dear students, it's teacher Walter. I'm back again with mathematics senior 6, and we are still on the unit 1 complex numbers, but we are so far with a lot of lessons that have passed here, and now we are with the exponential form of a complex number. Ladies and gentlemen, last time we heard a lot about complex number, and if you remember very well, in our last lesson, we talked about different things, and especially, ladies and gentlemen, we have seen the nth roots of a complex number and the nth roots of a unit. So, ladies and gentlemen, let us see the exponential form of a complex number. So far, we have seen different forms that a complex number can be represented with. We have seen first of all that a complex number z can be in the form x plus y I, and this we called it the Cartesian form of a complex number, which is also called the algebraic form. So these are two names that are given to this form. It's algebraic form or Cartesian form. Later on, we have seen that z can also be represented as x, y. This is the geometric form. This is now geometric form of a complex number. Later on, again after geometric form, ladies and gentlemen, we have seen again another form, which is z, which is equal to r cos theta plus I sin theta. We call this again this is the polar form. We also call it, ladies and gentlemen, trigonometric form. So we can call it either a polar form of a complex number, or we call it trigonometric form of a complex number. Now, ladies and gentlemen, here we are back to talk about the exponential form of a complex number. The exponential form of a complex number now will be of which form? So we shall see that it means that now the formula for the exponential form is given by what? By z, which is equal to r e power I theta, ladies and gentlemen. This is plus. So there's no need of putting this plus. If you leave it, it's fine, because theta is positive. So, ladies and gentlemen, what do you observe? You can see that if we have this exponential form of a complex number, what you need to find is just to find r, which is the modulus of z, which is normally found even in the exponential, in the trigonometric form. So we also need to find theta, which is the argument that we are also used. They are found in the same way, but what you just do is to put in this final form, and this is the exponential form of a complex number. And later on, we shall see that, and its conjugate. The conjugate of this one is it will be z bar, which is equal to what? Will be equal to r e minus I theta, ladies and gentlemen. And what do you observe? You observe that here what we have done is that change the sign here, which means that theta is negative. So the modulus remains the same for the conjugate and the complex number z, and the argument changed to the negative one. This is the opposite of the normal argument we have here for z. So, ladies and gentlemen, this is how we find the exponential form, and this is its conjugate. So, when we are going to find the exponential form of a complex number, we don't do anything else. We just find the modulus of the complex number, and we find theta, and then we get it. So I'm going to read you with an example which will help us to understand better on how we find the exponential form of a complex number. So, ladies and gentlemen, this is an example that we have. We have to express the complex number square root of 3 plus I in exponential form. And what you observed, ladies and gentlemen, you should have seen that there is a certain relationship between the exponential form and the trigonometric form. What is that relationship? Is that if we have z which is equal to r cos, if we have z which is equal to r cos theta plus I sin theta, and we have the exponential form which is z which is equal to r e I theta, there is a certain relationship. The relationship is that we all need to find r and theta. We all need to find the argument and the modulus. So here we have a complex number z which is here, and we shall find its modulus first, which will be absolute value of square root of 3 plus I. And as normal we are used for this will be equal to square root of 3 squared plus 1 squared. And ladies and gentlemen, this will be equal to square root of 3 squared. This is equal to 3 plus 1, and this is square root of 4, and this is 2, ladies and gentlemen. So I have here the modulus already of z, and now I have to find also the argument. If I am going to find the argument, ladies and gentlemen, remember that the argument of square root of 3 plus I, here because we have that x is square root of 3 and the square root of 3 is positive, is a positive number, then the argument will be equal to tan inverse of y which is equal to 1 square root of 3. And this will be finally, if we rationalize, it will be tan inverse of square root of 3 over 3. Now, it is like they're asking us which angle that its tangent is square root of 3 over 3, ladies and gentlemen. If everyone can see it, it's an angle where its sine is 1 over 2 and its cosine is equal to square root of 3 over 2. And this is none other than the angle 30, which is pi over 6 radian. So ladies and gentlemen, we have already the modulus and we have also theta, the argument. We can now write the exponential form of this complex number. So we shall see that the exponential form of z, which is equal to square root of 3 plus I, equals to what? This will be equal to r, which is 2, then e power I theta which is, ladies and gentlemen, pi over 6. So this is the exponential form of our complex number. And if I like it maybe better, it will be pi over 6 times I. So this is the exponential form of our complex our complex number z, which is equal to square root of 3 plus I. Nothing we have done is just find the modulus and the argument, as we do for trigonometric form. Then we express it in this form, and this is the complex number z. We can also be asked to find its conjugate in the exponential form. This will be what? A conjugate of this number will be none other than, of course, if we have its algebraic form, it will be square root of 3 minus I. And now in the exponential form, this will be 2e power negative pi over 6 times I. And then what change is just the argument, which becomes negative. Ladies and gentlemen, this is how we find the exponential form of a complex number. And now I will invite you to look through this and we'll be able to understand this, ladies and gentlemen. Now, ladies and gentlemen, from this, using the relationship between the exponential form and the trigonometric form of a complex number, we can find now the modulus and the argument in this way. Let us go and see. So, ladies and gentlemen, you will see that if r equals to 1, ladies and gentlemen, we shall see that we shall have e, which is power I theta. E, which is power I theta, means that r is 1, and the argument is theta. This means what? This means that this is the same as R is 1, there's no need of writing it. We should just have cosine theta plus I sine theta, ladies and gentlemen. These two things are the same. This is exponential form, this is the trigonometric or the polar form when R equals to 1. Now, looking at its conjugate will be negative I theta, ladies and gentlemen, and this is the same as writing cosine theta minus I sine theta, ladies and gentlemen. Now, we can find now the real part and the imaginary part for these things. How do we find it? We do this. So it's like here we have 1 and this is expression 2. So ladies and gentlemen, if I find 1 plus 2, it's better to follow here. This is very important. And then we have, ladies and gentlemen, e power I theta plus e minus I theta, which will be equal to what? To this plus this. Now if we add this, ladies and gentlemen, you will see that this will disappear and we shall remain with this. So we shall get now 2 cosine theta, ladies and gentlemen. Now, through this, we shall now get what? Remember, we are looking for the real parts and the imaginary part. And the real part on this side is cosine theta, and the imaginary part here is sine theta. So how do we get now cosine theta here? So getting now this cosine theta, ladies and gentlemen, will be equal to e power I theta plus e power negative I theta over 2. Thank you very much. Now, we can also do something else. We can also find 1 minus 2, ladies and gentlemen. If we take the expression 1, we subtract it to 2, we shall get now e power I theta minus e power negative I theta, which will be equal to what, ladies and gentlemen? I now take this minus this. If you see very well clearly, this will disappear. And then, because the signs will be negative opposite. This is cosine theta minus cos theta, which is 0. Then we have I sine theta negative I sine theta, which will make it I sine theta plus I sine theta, and this will be, ladies and gentlemen, to I sine theta. I'm sure everyone can see it. Now, we are again having a purpose to find sine theta, which is the imaginary part. This was another way to find the imaginary part and the real part of a complex number in the polar form. So this will be sine theta, which will be equal to e power I theta minus e power negative I theta over 2I, ladies and gentlemen. Now, here we have now very important formulas. You can see these two formulas. These formulas, we use them to do something very important, which is called linearization, which is coming after this lesson, which will be in our applications of complex numbers. So these formulas, they are called, these are the Euler's formula. These are the Euler's formula, which we use in linearization of trigonometric expressions. So we shall come back to this as an application to see how we use these two formulas, the Euler's formula, in linearization. In linearization, we use these two formulas. So, ladies and gentlemen, I will leave you with a small work that you will do, and after doing it, you will be able to express the complex numbers I'm going to give you in the exponential form, and there is nothing you have to do rather than finding the modulus and the argument. You find just the argument theta and the modulus r, and you just express in exponential form. Then this will come later on when you go for applications. Ladies and gentlemen, I'm going to leave you with a small work that everyone will try to do, and it will be very useful to you. Ladies and gentlemen, I will ask you to express, this is a homework that everyone will try to just evaluate his understanding about this lesson. So you have to express the following complex numbers in the exponential form. In exponential form, ladies and gentlemen. Number 1, you have, ladies and gentlemen, z which is equal to 1 plus I. You will express it in exponential form. To express it in exponential form, you just find theta and r, the modulus and the element. And ladies and gentlemen, here you get an answer which will be equal to z which is equal to square root of 2 e power pi over 4i. Ladies and gentlemen, you can also try this, number B, which is z which is equal to 1 minus I. And here you will get an answer which is z which is equal to square root of 2 e power negative pi over 4i. Ladies and gentlemen, this is the work I left you with, and everyone will try it as a homework to just see whether you are understanding our lesson. Thank you very much. I'm just inviting you to follow us on our website, which is none other than www.umenyi.net, where you will find a lot about our lessons we have already given on our videos, previous videos, and you will find there notes, a lot of exercises, and more explanations, and they will help you to understand. If not satisfied, you will go again to our YouTube channel, which is Ikaramu TV, where you will get all the videos that have passed here before, and we'll be able to upload, to download them. And I just invite you to remember to subscribe for you to get all the following videos, and don't forget even to share for your friends. Thank you very much. It was Teacher Walter. I love you.